Now, we will calculate the magnetic field produced because of the current carrying coil. Suppose this is the coil, then coil's own axis will be this way. This is how we define own axis. Coil is this in horizontal plane, then own axis is going to be this way. That means own axis passes through the center of the coil perpendicular to its plane. Here we have considered a point on the axis of the coil. Suppose it is at a distance x, then magnetic field would be given by mu naught I upon 2. This is r square upon r square plus x square whole to the power 3 by 2. This is the magnetic field at a distance x on the own axis itself. By changing different values of x, you see x is variable here, that is the distance of point on the axis from the center. So, if you put the value x equal to 0, obviously you are at the center of the coil. In that case, the magnetic field become mu naught I upon 2r itself. Had it been half circle, it becomes half of this value, that is mu naught I upon 4r. Both things have been given over here. But one very interesting comparison is here, that you know the value at the center, this one, and value at a distance x. You want to find the ratio, it is going to be 1 plus x square upon r square to the power 3 by 2. Now, suppose instead of one turn in the coil, you are going to have n turns, then in that case the magnetic field is going to be mu naught n I upon 2r. This is the field at the center of the coil, but in that case number of turns will be n. You have to remember that field when you are talking about magnetic field by a current carrying coil, the field is going to be normally straight perpendicular to the plane of the coil at the center. But soon as you go away from it and you approach the periphery of the coil, you see it becomes in the form of concentric circles. You should also know how to decide. We have already decided that when current flows through a coil, it behaves like a magnet. And when you talk about magnet, obviously you must be knowing the poles. You say that this is the current carrying coil, obviously it is behaving like a magnet. One side should be north, other side should be south. It is a very interesting south, letter first of south. It is going to give the hint. You write in little artistic manner. For a moment you think of yourself being an artist and think of writing S artistically. You see, this idea will emerge automatically clockwise. So, let us join the two things. If the current appears clockwise from a particular direction, you consider that south pole. Likewise, if you write this letter N, that is first letter of north, you write this letter in artistic manner, you will find that anti-clockwise, the side from which this current appears anti-clockwise will behave as a north pole. These two rules, you might say shortcut rule, we are not assigning any name or the credit does not go to any particular scientist for this. But then we do remember, and that is very important, that if the current appears clockwise, that is south pole. If the current appears anti-clockwise, that is north pole. And now finally, I will consider a long wire, say length is L, and this wire has been converted into a circular coil having n turns. So, obviously, that particular length L has been converted into this thing, means radius of the coil becomes L upon 2 pi n radius. Now, you want to find the field at the center of the coil, and relation you know for n turns, this is mu naught n I upon 2r. It's mu naught I 2r n, and in place of r, mu naught, this is I, in place of r we would write here L upon 2 pi n. You see 2 gets cancelled, this is mu naught I pi n square upon L, this is V. What's important here is that B is proportional to n square. Magnetic field is proportional to n square. It's a parabolic relation. If you just try to find a circular coil of n turns, n might be 2, 3, 4 depending on your choice. But if you want to find number of turns in the coil, the magnetic field at the center of the coil is going to increase parabolically. This relation has been plotted over here.